Hey everyone, welcome back to my channel. In today's lesson, I am going to show you how to solve a tricky exponential equation in two different ways. Exponential equations can be challenging, but with a little bit of practice, you'll be able to solve them with ease. In this video, I'll be carefully showing all the steps and explaining the thinking process behind each method so you can fully understand the concepts and apply them to similar problems. So let's dive into it. The first thing that we are going to do is to review a very important property of equality of logs. We will apply this property at the very start of the first approach. Suppose that we have that u is equal to v. Then, if that's the case, the log base b of u is equal to the log base b of v. In other words, we can take the log of both sides of the original equation. Here we have the equation that we're trying to solve. The question says, solve the following equation in two different ways, and then to leave the final answer in terms of logarithms. We're going to go ahead and we're going to do two approaches. The first approach will be a little bit lengthier than the second approach. With the first approach, we will apply the property that we just discussed, the one that says that if we start with an equation, if u is equal to v, imagine that the left side is u and the right side is v, then we can consider the log of both sides as long as we keep the same base. I'm going to use here base 10, the common logarithm. So imagine, on the left side, I'm going to take the log of the left side, and then on the right, same thing, the log of the right side. So that's what I have. Now, I want you to notice that I have a product. I have 3 to the exponent 1, and then I have a power 2 to the x minus 2. Since the exponent here only belongs to 2 and not to 3, I cannot bring the exponent down right now because x minus 2, the exponent, only belongs to 2, not to 3. So then, since I have multiplication, it is better to expand by using the product rule for logarithms. That means that I'm going to have the following. I'm going to have log of 3 plus the log of 2 to the x minus 2 equals to the log of 6 to the x. Then in this particular case, this term pretty much is there. Nothing much will be done to that term. But this one here, now I can use the power rule for logarithms, the rule that allows me to bring x minus 2 down. I can bring it here in front of the log, and then it will multiply the logarithm. Same thing on the right. I can bring this exponent down, and it will multiply the log. So then, applying that rule or property, we're going to have log of 3 plus x minus 2 times log of 2 equals x times log of 6. So notice how the exponent here was brought down, and you see it right here in front. And then the same thing happens here. Now, remember that log 2 is a real number. There's no variable here, just log 2. If you were to punch this in your calculator, you're going to get a decimal approximation. Same thing with log 6. That's a number. So log 2 and log 6 are like the coefficients right now. And like any coefficient, I can now use distributive property. For example, I can take log 2 and multiply it with 2 and with x. This is precisely distributive property. That means that I'm going to have log of 3 plus x times log 2 minus 2 log 2 equals x times log of 6. So that's what I have right now. Now I want you to notice that I have a bunch of terms, but there are some terms that are like terms. For example, if I look at this one right here, this term and this one, those are like terms. Again, remember, log 2 and log 6 are coefficients, and they are coefficients of the variable x. So I can actually put them together on one side. I will take this one and move it over to the right. Or it's like saying that I will subtract this term on the left side and the right side. So we're going to have log 3 minus 2 log 2. Those two terms will remain on the left side. Now I'm going to bring x log 2 to the other side. So then we're going to have x log 6 minus x log 2. So I want you to notice here, look at this. Here is my variable x, same variable x. So I can factor x out. That means I'm going to have log 3 minus 2 log 2. The left side remains the same. But now I can factor x out, and I'm going to have log of 6 minus log 2. Very nicely. And again, these are real numbers. That means that I can go ahead and I can divide both sides by that difference. In other words, I can do this. I'm going to have this, and I'm going to divide by log 6 minus log 2. And the same thing here, log 6 minus log 2. Perfectly. Everything will divide out here. And now, continuing, now we are going to have in the numerator log of 3 minus. I want you to look at these two right here. This coefficient, I'm going to move it up as the exponent of 2 by applying the same property of logs that we used in this step right here. In this step, we move the exponent down in front of the log. Now that I have this number in front of the log here, I'm going to move it up. So I'm using the property in reverse. That means that I'm going to have log of 2 squared divided by log of 6 minus the log of 2. And then simplifying a little bit more, instead of having 2 squared, I'm just going to say 4, and all this over the log of 6 minus the log of 2. So that's a good enough answer, but we can go ahead and condense a little bit further. See, in the numerator and denominator, I have a difference of logs, and I can condense each of those differences by using the quotient rule for logarithms. I'm going to go ahead and do that. So in the numerator, we're going to have log of 3 over 4. And all this divided by the log of 6 divided by 2. And I can do one more simplification. Let me continue here. We're going to have that x equals to the log of 3 over 4 divided by log of 6 over 2, just 3. And there it is. This is the final value for x. That means that we have solved the equation. Now we're going to go ahead and follow the second approach. And you're going to see that there will be a slight difference into how we're going to go ahead and solve for x, but we should get pretty much the same answer. So what I am going to do here is to begin by breaking this power into two separate powers just by using properties of exponents, just like this. I'm going to write 3 times 2 to the x times 2 to the negative 2. This is going to be equal to 6 to the x. Then we're going to take this power here that has a negative exponent and turn it positive. That means that we're going to have 3 over 2 squared. I'm going to move the power together with 3 times 2 to the x equals 6 to the x. And now we're going to have 3 over 4 times 2 to the x equals 6 to the x. Now what we are going to do is take this power right here, and we're going to divide both sides of the equation by 2 to the x. For example, I will divide the left by 2 to the x, and then to balance the equation, I will do the same thing on the right. Okay? And now notice how here 2 to the x will divide each other out, and then we're going to have 3 over 4 equals, and then having 6 to the x over 2 to the x is the same thing as just bringing the exponent up over the entire fraction, 6 over 2. Okay, so 6 to the x over 2 to the x is the same by rules of exponents as 6 over 2 to the x. And that is going to nicely give us now 3 over 4 equals 3 to the x. Now, in order to continue here, we will take this exponential equation and we will express it in terms of logarithms. For example, this is equivalent to saying that the log base 3 of 3 over 4 is equal to x. And honestly, this is a good answer as well. But if you remember, the previous answer that we got had a logarithm of base 10. Here, we have a logarithm of base 3. So then, if we insist on the two numbers looking exactly the same, then all that it means is that we're going to have to go ahead and continue working this out by changing to base 10. But as it is right now, this number is identical to the previous one that we got in approach number 1. They look different, but as a value, they are exactly the same value. They just look differently. But I want to show you, though, how to make them both look identical, particularly this one. I want to show you how to make this one look identical to the one that we got in approach number 1. But in order to do that, I need to introduce you to the change of base formula. Folks, here is the change of base formula. The formula says that if I have a log of base b of x, I can always change to any other base as long as I follow this rule. So if I want to go from base b to base c, and c can be any potential base, then that is equal to the log of the new base c of the input x. Notice how the input remains the same. And then in the denominator, we have the log of the new base of the old base right here. So log base c of x over log base c of b. If you remember again, in approach number 1, we were using base 10. So then I'm going to now go ahead and apply that change of base formula, but c is going to be 10. And when the base is equal to 10, I don't even have to show it. If we don't show a base, it is always assumed to be base 10. Okay, so in this case, we're going to have that x is equal to log of 3 over 4 divided by the log of 3. And there it is. this is exactly the same value or expression that we got in approach number 1. So you really see how these two numbers are identical. The only thing is that this one here was in terms of base 3, but then that was perfectly equal to this other expression. Just a different look. All right, folks, I hope you found this lesson helpful and informative. Remember, solving exponential equations can be challenging, but with practice and patience, you'll be able to do it too. By understanding the steps and the thought process behind it, you will be able to solve not only this equation, but also many other similar problems in the future. If you have any questions or suggestions for future videos, feel free to leave a comment below. Don't forget to like and subscribe to my channel for more content like this one. Thank you for watching, and I'll see you in the next video. Bye, everyone.